As of recently, it appears that everyone is attempting to predict when and how the world might end. Some scenarios are far more recognizable and plausible than others. These commonly discussed threats in the media range from pandemics to nuclear conflict, and even asteroid impacts. Though vastly different, they all share one core similarity. Each has the potential to wipe out humanity completely. But all of these situations pale in comparison to one thing: black holes. We've all heard of them, but what truly is a black hole? Black holes are zones in space where gravity becomes so extreme that the fabric of space and time folds inward, taking all exits with it. But what does that really mean? And why are black holes dark? Every large object, like a planet, star, or black hole, has an escape velocity, which is the speed needed to overcome its gravity. For instance, Earth's escape speed is around 11 kilometers per second. Travel that fast, and you could leave Earth and drift into the cosmos, though you'll eventually be pulled by some other gravitational force. That's beside the point. The stronger the gravity, the greater the escape velocity. Black holes have some of the most powerful gravitational pulls in the entire cosmos. They're believed to contain singularities, points where gravity becomes infinitely strong. But we'll explore that soon. Let's imagine we somehow form a black hole with the same mass as Earth, roughly 6x10 superscript 2 kilograms. Looks good, but not to scale. It would appear more like this. To turn Earth into a black hole, you'd have to compress it down to roughly the size of your pinky finger, about 9 millimeters wide. So, both objects have the same mass, one is a planet, and the other fits in your hand. How is this possible? Black holes typically form from the collapse of massive stars, those around 20 to 30 times more massive than our Sun. While alive, stars perform nuclear fusion, fusing lighter atoms like hydrogen and helium. This reaction produces energy and outward pressure, countering the pull of gravity. Over billions of years, stars run low on these lighter elements and start fusing heavier ones. They begin fusing carbon and oxygen, eventually reaching silicon and iron. Here's where it gets tricky. Iron can't fuse with other elements. No more energy is made, and gravity takes control. The star then collapses under its own weight and explodes into a supernova. The outer layers are blasted into space. Meanwhile, the core compresses further and further. Remember Earth's escape velocity, 11 kilometers per second? Well, after the collapse, if the core is still massive enough, about 2.5 times our Sun's mass, and extremely dense, its escape velocity surpasses even the speed of light, over 300,000 kilometers per second. This marks the birth of a black hole, a region in space where not even light, the fastest thing we know, can escape. But let's make this fun. Let's fall into one. Picture yourself aboard a spacecraft, not just any, but one that can defy physics. It can accelerate to unimaginable speeds, even faster than light. Impossible, yes. But this is your ship, unbound by reality. You're fearless and head straight for a black hole, all in the name of science. You choose Sagittarius A/**, the supermassive black hole at our galaxy's center. This giant spans over 88 million kilometers across, nearly 100 times wider than the Sun. Its size means you'll have time to experience it as you descend. At first, things may seem calm. Here's why: due to its massive size, the gravitational pull isn't painful, yet. But you'll start noticing strange things. As you approach, the stars behind you brighten. Their light bends and shifts blue due to the black hole's immense pull. As you get closer to the event horizon, the boundary between our universe and the black hole, your view fills with darkness. It seems as though the entire front sky has gone black. Right before crossing the event horizon, you'll see the rest of the observable universe collapse into a tiny point behind you. Zoom in, and you'd see stars, galaxies, and even a faint red glow. It's the cosmic microwave background, the radiation left over from the Big Bang, now boosted into visible light. Then suddenly, black. You've crossed the event horizon. There's only darkness now. You start your mission, ready to study what's inside before being torn apart. But you find nothing. No light. Your view is pure, total black. You began this journey to uncover the mysteries of a black hole's core. But there is nothing. The singularity lies ahead, where our science and math no longer work. You hope to solve it, but the answers are unreachable. You try to turn back, firing your engines at speeds beyond light. But your instruments are acting strangely. They should point toward the singularity, helping you escape. Instead, they indicate it's in every direction. Gravity grows stronger in all directions, left, right, up, down. The spot you're in is the least intense gravity you'll ever feel again. Any path takes you closer to the core, and death. You doubt your sensors. This can't be right. But it is. Once inside the event horizon, there's no way out. Our 3D coordinate system breaks down. Time doesn't flow as it does out here. Time now moves downward, toward the singularity. The curvature of spacetime inside the black hole bends every path inward. Every possible direction leads only deeper. That's what an event horizon really is. A boundary beyond which all directions lead inward. The singularity surrounds you. And it's getting closer.